Hey, can everybody hear me okay? Awesome. All right, hey everybody, welcome to this Formlabs webinar on supports orientation and lasers, understanding SLA 3D printing. My name is Jordan Pelovitz. I work with the customer success team here at Formlabs. It's my job to make sure our users, both internal and external, have the info that you guys need to print well and troubleshoot effectively. So first, a little bit about us. If you didn't already know, we're Formlabs. We're based just outside of Boston, Massachusetts. We're formed in 2011, and our first product, the Form1, was launched on Kickstarter in 2012. And that gave us that first boost into production. After that, we announced an upgrade kit, and then in 2015, we released our current flagship product, the Form2. And then after that, we rolled out several functional resins, including Dental SG, in early 2016, and that made us the first and so far only desktop SLA 3D printer with a biocompatible resin offering. So we prepared a lot of content today to give you folks an insider look at the Formlabs development process, and by the time you walk away from this webinar, we'd like you to understand not only our process, or our SLA process, but also SLA processes in general, and also understand potential print orientation concerns, so things like islands and suction cupping. If you don't really know what I'm referring to yet, don't worry, we're going to get into that in a little bit more detail, but like I said, we've got a lot of info, so let's stop talking about what we're going to learn about and just get into learning it. So we're going to start with a brief overview of SLA as a process. What you're looking at here is a diagram of the traditional way of doing SLA. A laser fires into a reflective mirror that's above the tank, which bounces it down into a vat of liquid resin below. The first layer, of course, starts on the build platform, and then once that laser finishes hardening the layer, the build platform moves down, and that sweeper glides across to clear off any debris or residue or anything like that, and then the next layer occurs. So that's the general core of how a traditional SLA process is done. Of course, the resin itself is photoreactive, and it was originally, that process was first pioneered in the 1970s by Japanese researcher Dr. Hideo Kodama, and he was the first one to develop the process of using UV light to cure photoreactive resin. And after that, Chuck Hull of 3D Systems coined the term stereolithography in 1986, and the rest is history. He founded 3D Systems, and it's continued to grow. The technology has continued to grow from there. You can actually still see some of that influence of the early innovation today. STL files, the standard format for every 3D printer out there, every CAD/CAM machine out there, that actually stands for stereolithography. There's a bunch of acronyms like standard tessellation format, but the core of that is stereolithography all the way back in the 80s. All right, so I got a question for everybody here. Take a look at these machines and think to yourself, what about them looks functionally or visually similar? What about them ties them together? The answer would be, if you said they were inverted, you'd be correct. No idea what the point of purpose of this car is. I'm just amazed that it exists. It's a real thing. I found it on the internet, and it actually works. So there's that. Anyway, so the big thing, the inverted SLA platform allowed the printer, the Formlabs machines, to use a lot less resin, and it's one of the key components that allowed us to bring SLA to the desktop market, to the prosumer market. So think about it this way: if you have a traditional SLA setup and you want to print a 12-inch tall soda can, so your build volume is 12 by 12 by 12, and you want to build a soda can that's 12 inches tall and 4 inches in diameter, you're actually going to need 7.5 gallons of resin in the tank in order to print that, because the build platform has to completely submerge the part in the resin tank. Then on top of that, you have to have a 24-inch tall or more printer so that the part can completely raise out. So again, the inverted build process that we pioneered is one of the main reasons that the printer is so successful on the desktop. So on the next slide, we have an example of a traditional, SLA machine. They have to be really big. They have to be really bulky. They're sensitive to vibrations. If your coworker's walking around after that 3 p.m. like lunch coma and he's stumbling around, then that vibration is going to affect the machine. So they have to be very large to dampen that. In addition to fitting the build volume. On top of that, they also require trained operators. They don't really take advantage of kind of the new advances in user experience design that some other machines may do. So to introduce some of the other systems that make the Form2 work, we have the short video that we put together for the machine's launch. I'm just going to show a brief clip of that. If it loads. There we go. Okay, so like the video said, we have a laser. It's not Iron Man powerful, but it's pretty powerful. It's the core of our optical engine. It's what the whole machine is built around. So I'm going to start with that, and then we'll get into some of the other systems. So the Form2's laser is a 405 nanometer, so that's 405 nanometer wavelength laser with a 250 milliwatt power output. You can actually pick up handheld versions of this type of laser from anywhere from between $5 and $240 on the internet, depending on quality and power output. But it's really useful to have these around the shop because you can actually dab some uncured resin onto your part, and then if you hit it with the handheld laser, the laser will cure the resin. You can actually use it like a sort of glue for your printed parts. So if you ever have to split up a part or something to fit it into the build area, it's a good idea to have one of these lasers around. So on the topic of laser power and wavelength, you can see the testing equipment that we actually use to make sure the Form2 laser would stand up to the abuse of industry on the bottom right down there. To simulate thousands of hours of printing, we run the lasers at a higher than normal temperature for hours or days and record the laser spot, which is what you can see above it. So we use specially designed cameras and sensors to analyze and record that laser spot to ensure the beam satisfies size, shape, and power metrics. On the left, what's with the big gradient curve over there? It's not our exact power and curing profile, but it shows a critical bit of information about our laser, which is namely that despite the laser's diameter being only 140 nanometers across, or 0.14 millimeters, it still cures in a gradient. So that focus of curing is in the center, and then it kind of gradiates out from there. If you take a look at the beam profile in the top right corner, you can actually see that as there as well, with the red in the center, and then it goes out to green and then blue and then eventually purple. So this is actually really important because when we design our galvo control mechanisms, we take this into account so that when the laser passes over each beam path, we're spacing them so that the beam can not only cure the current layer, but part of the previous layer as well. And that gradient is one of the main reasons why SLA print processes have such a smooth finish versus FDM, where it's a hard on-off sort of thing. So on that note, speaking of galvanometers, one of the most critical updates we made to the Form2 was actually design and develop our own galvo system. A galvo is basically like a faster, higher precision electric motor, at least in our case, where we put a small mirror on the end of it and use it to redirect laser beams, which sounds cool when you say it. So these small devices create a rotary movement when electrical current passes through a coil inside a stationary magnetic field. So in the big image on the right side of the screen, you can see that part of the magnet that creates that stationary magnetic field is cut away, and you can see the coil inside of it. So on the bottom left, you can actually see the test rig that we used. The galvo control boards are the big green circuit boards below it, and then above them is the clevis that actually holds the galvo. And basically we run them for hours and hours and hours, just making sure that they'll actually stand up to use in the field. So the PO operation is another critical component of any inverted SLA or DLP process, and it's one of the biggest areas that we look to improve on from the Form1 Plus. The PO operation basically is there to remove the freshly cured resin from the bottom of the tank. So if you think about it this way, when your part is cured, it's cured to both the build platform and the bottom of the resin tank. So that sliding mechanism that's in the Form2, or the lever action that's in the Form1, is there to remove the part so that the build platform can raise up and the next layer can be printed. So the big reason, so what we did here, and you can actually see this on the left, is we prototyped a bunch of different operations to try and figure out how to improve the peel process. We even actually implemented some ideas using the Form1, which what you're looking at right now is the first prototype for the Form2's peel operation. But what we even decided to go with the lever action, et cetera, but what we decided to end up with is the peeling system that you see today. So without complicating things too much, we also decided to add a wiper. We didn't do it without a reason. The basic purpose of the wiper is to stir up the resin and oxygenate the PDMS layer. So I just said a lot of letters. PDMS stands for polydimethylsiloxane. I'm not sure if that helps. It's basically silicone at the bottom of the tank, and it's fairly inert. It holds oxygen well, and it's somewhat flexible, so it can handle any perturbations caused by the peel operation. So when the part's being pulled away from the tank, the PDMS layer at the bottom of the resin tank actually flexes slightly to allow that to move. So the wiper's main purpose there is to stir the resin so it maintains a constant consistency that prevents gooping or globby resin spills on your parts. It also removes any bit of resin that might be stuck on the PDMS, and then finally, when I say it oxygenates the PDMS, it's basically exposing this layer of silicone to the air so it can soak up some of that sweet, sweet O2, and that allows the print, so when the part cures, it's actually curing slightly above the PDMS on top of that oxygen layer. So that's one of the big reasons that we include the wiper, because it reduces peel forces and increases print reliability. So the next stop on our little systems adventure is the tank heater. This little guy exists to make sure that the resin is at the proper temperature, and that's directly related to viscosity. So the wiper's velocity, we calculate it based on what the known viscosity of the resin is at a certain temperature, and we have those temperature listings online. So that's actually, if any of you have used open mode, that's one of the reasons that we disable both the heater and the wiper, is because we don't know the viscosity of the resin that you're putting into the resin tank. So if it's if it's not viscous enough and the wiper moves too quickly or the tank heats it up too much, then it could spray out into the rest of the machine. That could damage your part or your machine itself. So that's again why we disable those functions. So the big operational thing for this is just please try not to print before the tank is fully heated. You can do it, just print like close to when it's almost ready if you're going to start. Especially in colder climates like in Boston, it's a real concern. So it's up to you, but you know, that's what it's there for. So finally, we come to the last pillar of SLA printing, which is the resin or the photopolymer. Different companies have different formulations, but most work on the same basic principle, which is that short chains of oligomers or monomers are floating with photoinitiators inside the resin. These photoinitiators are excited by the UV light, and then they send out free radicals that cause the monomers and the oligomers to bond together to form polymers. So if you don't know chemistry, monomers and oligomers are short chains of connected molecules, and polymers are longer 2D or 3D chains of those same molecules or atoms. In addition to the oligomers, monomers, and photoinitiators, the resin might also contain visual and or functional additives like color and castability enhancements. So in a little more detail, resin is a plastic composed of those molecule chains, and it's made up, and it's has all the final properties of the final plastic, but it has not been fully polymerized or cured. So once an SLA resin is cured via UV light, it's chemically bonded, and that's why that's why photopolymers are considered to be thermoset plastics. And that means that basically once they're cured, the matrix is irreparably changed. You can't melt it down again and use it. Once it's basically cured, it's done. That's opposed to thermoform plastics like PLA or ABS, which are not chemically changed on bonding, and those can actually get melted down and reused. The difference here, one of the other big differences, is that SLA resins are better for making watertight parts, because the entire component, once it comes out of the machine, is chemically bonded and unified. So there's no discrete layering, essentially. Whereas in an FDM machine, each layer is mechanically bonded through heat, but it's not a single part. They're still discrete mechanical layers. So during the polymerization process, we're zapping the resin with UV light. The light activates the photoinitiators. I already explained how they'll split apart. They'll send out free radicals into the system, and those will cause the oligomers and monomers to be attracted to each other. There's two main variables when we design our resins. There's the energy of cure, which is the amount of laser energy required, and then the penetration depth, which is how far the laser can actually penetrate into the resin. So you can observe some of that testing for penetration depth there on the far right. The energy of cure is controlled by the photoinitiator, while the penetration depth is controlled by blocker elements that we also suspend within the resin. So one key thing that we recommend for all users to investigate is a good post-curing solution for their prints, for your guys' prints. Really, after the print, the polymer is still not fully reacted. There's still lots of little reactive groups hanging around, and the polymer is still technically considered to be green. So by post-curing that polymer, we are completing that polymerization process to a much higher degree, which makes it much stronger and less sticky. So the charts on this graph are measuring tensile strength, which is the resistance of a material to breaking under elongation. You can see testing rig on the right side. Basically, you take a small sample and you pull it until it pulls itself apart. And you can see the chart on the left there, that's showing different laser frequencies at the same temperature, while the chart on the right is showing the same laser frequency at different temperatures. And you can see that 405 nanometer wavelength laser, which is the same, 405 nanometer wavelength UV light, and 60 degrees Celsius, you get a huge increase in part strength. So this is really critical for functional components like tough resin or castable resin and stuff like that. So If you'd like some instructions on how to build your own cure box, you can check out our support site at formlabs.com/support. Under finishing, you'll find a section on post-curing prints. It's roughly $30 to make your own cure box, and the results will definitely speak for themselves. Okay, so let's finish up talking about subsystems with review. We have a 405 nanometer wavelength laser that fires through the bottom of the printer to cure the resin. The laser is directed by galvanometers, which are small devices that create a rotary movement when electrical current passes through the coil inside a fixed magnetic field. Those galvos are faster and more precise than regular electric motors. That's why we use them. The laser hits the bottom of the resin tank and cures the resin in a gradient, radiating out from the laser's center, the center of the laser's focus. And that means that layers are more smoothly transitioning into each other and are not stepped, which affords us that smooth finish that's typical of SLA parts. Then the sliding mechanism peels the part off the bottom of the tank so that the build platform can raise up and allow the wiper to slide across. And the wiper's primary purpose is to mix up the resin and aerate the PDMS, which thus reducing peel forces. The resin then itself is called a photopolymer, and then it chemically changes once it's cured. We went over that. Parts are unified and not made of discrete layers. So that's something really critical to understand, is that when you get a Formlabs or a part out of an SLA machine, like a Formlabs printer, it's a single block. It's not, there are no individual layers in that sense. Okay, so as we shift from systems to usage, I'd like to share with you some tips and best practices to help keep your printer healthy, happy, and gunk-free. The first thing I recommend, and I'm guilty of breaking this myself, is to first remove the resin tank, then remove the build platform. The reason for this is because if your build platform has any uncured resin still on it, once you remove the resin tank, that can drip into on top of the optical window or on top of the main mirror itself if you're using a Form 1. And it's no fun to clean that up. I've seen some interns do it, and it takes them quite a while. You should clean small resin spills with IPA. Try not to put any IPA on the orange plastic, and if you do, only a small amount, because IPA will cause the plastic to craze and or crack, which will reduce both its functional properties and its aesthetic values. Finally, when you're removing the tank, you can actually, we recommend holding onto the wiper with your thumb and forefinger. So of course, remove the wiper first, then remove the tank. But when you're removing it, kind of hold onto that wiper in case it flicks backwards and sprays you. And then finally, once you take all of that out, you can actually use the plastic lid that came with your resin tank, so you can keep your wiper, your resin tank, and your build platform all together. There's actually an indent on the top of that plastic lid that allows you to hold onto your build platform. Okay, so next, don't refill cartridges. This is, we really don't condone it. That's one of the big things. When I first started working here, everybody kind of gets a printer for their desk. I let someone else use my printer, and they used a recycled cartridge, and it dumped 2 liters of resin into my printer. The bite valves on the bottom of the cartridges are only rated for 1 full use, and then the cartridge is technically done. So we really recommend avoiding refilling your cartridges. I still haven't seen the printer. It's in refurb somewhere. Of course, you can contact us anytime if you have any questions. The last thing I'll mention here is to avoid resin contact on your skin. It's not poisonous, but over time you can build up an allergy. And then, of course, when you're cleaning it off, be careful with large concentrations of IPA, and don't use IP on your skin to clean resin off. It actually dissolves the resin and makes it easier for your skin to absorb it. So just wash your hands off with soap and water. Okay, so that's a ton of info. Let's take a moment to breathe, let it all sink in. We're going to get into some nitty-gritty detail next, so everybody chill out, and we're good to go. Okay, so supports are similar to a suspension bridge. That's why we have this image here. If the part is basically hanging from the supports above them, rather than in many other processes like FDM, where the part is resting on top of its supports. And this is a critical area that we find a lot of confusion for most users because it's so different than other standard systems. So let's first start with some vocabulary. The base is this large footprint that's compressed onto the build platform, and it serves to anchor the part. We've included these small little raised features on the base to make it easier for you to get the release tool underneath and pry it away. Those are the quick release tabs. And then moving upwards, we have the scaffolding. That's auto-generated and interlinked. It provides structural rigidity. And then those terminate in the touch point or the tip, which is the point of the scaffolding that actually touches the part. So you can see on the image on the right there, each of these touch points is actually supporting a circular area around the point itself, note that the size of the touch point doesn't actually increase or decrease that circle. That circle is standard no matter what the diameter of your touch point is. The reason we change the touch point diameter is to increase or decrease the strength of the bond, not the influence of the bond. However, what you can see here is you can see that that block, even though it's supported by only a single touch point, the top and maybe a little bit of the sides are actually gray as well. And that red is showing you preforms like, hey, you might want to add some supports. I'm not sure if this will work. And what we're seeing here is we're actually seeing that influence radiate outwards. And that brings us to the person on this slide. So the red cones in the detail view of this model show us the force that preform exerts, and it exerts it in a conical shape, emanating outwards from the touch point. Excuse me. When the model has enough support touch points so that the cones in the circular areas overlap, the mesh is considered to be fully supported. So you can kind of think of your model like a sheet of fabric that's hanging from supports. If you take your thumb and forefinger and pinch your shirt on the shoulder and pull up, you'll get a similar sort of effect. So if your touch points are too far apart, you'll end up with a scalloped effect. We call it bat winging, where your part actually sags under its own weight between the supports and you get that scalloping effect. So when you're placing your supports, try and visualize the forces that the part will be undergoing. So like slide-to-side peeling motions, gravity pulling downwards, any sorts of twisting and bending motions that you could see yourself exerting on the part in order to break away the supports, and then try and factor that in when you're actually determining your support placement. One other thing is definitely don't go too gung-ho with your supports. So I just told you, don't space them too far out. Also, don't put them too close together. So keep an eye out for more than 10 supports in a 5 to 10 millimeter radius, because what you're essentially doing is if you have that many supports in a closed area, you're keeping resin from flowing through. Essentially, the supports are creating a forest, and it's stopping the flow of resin. And that can be a problem because it can actually either cause your part to delaminate or cause the laser to fail to harden the resin entirely. Okay, so let's talk a little about orientation, which is the other side of the support coin. If we take a look at the two images on the slide here, the one on the left shows the incorrect way to orient a large flat object, while the one on the right is showing the proper way. So there's a couple factors at work here. You have to worry about the peel process, the structural rigidity of that semi-cured resin, as I just went over, and then the finishing process that you're going to have to go through in the end. So by laying the part flat, you're creating a large flat surface up against the resin tank that's going to get pulled down or yanked to the side. And so when the print is still in its very early stages, that layer may only be a ½ millimeter thick or less. So it's really susceptible to warping and tearing during the peel operation, especially if you have this big surface area that's only held up by these tiny little supports. So in addition, if you remember, we talked about that bat winging effect. With a long flat piece like this, you have a ton of surface area, a ton of little supports, you're more likely to see that effect. You could increase the amount of support touch points, but that could either make it so you have an unbearable amount of sanding to do after the fact, or again, we could run into that problem that I talked about before where it inhibits resin flow. So cases like these, with a long flat component, and in general, you should tilt your part up like in the second image. That's reducing the peel forces, reduces the amount of supports you need, and the general rule of thumb here for orientation is that you try and have as much of your part build off itself as possible and minimize each layer's surface area that makes contact with the bottom of the resin tank, thus reducing those peel forces. So let's get through the images on this page, and then we'll jump into the practical demonstration. On the far right, what we're trying to communicate here is that all long parts should be oriented so that the long side is parallel with the front of the machine. The reason for this is it's reducing the stress on the part caused by the peel operation, and it's allowing the resin to flow more easily around the part. This is especially important if you're using a Form 1 or a 1+, because the lever action creates a downhill movement of the resin, and it's really critical that you follow this rule. Finally, and this is a big one that most people don't catch until it's a couple prints after the fact, and they failed several times. We have an enclosed area that's creating a suction effect, and then yanking the part down, causing a partial or complete print failure. So if any of you have ever played with a Nerf gun or seen an octopus latch onto something, it's a similar effect, where an enclosed cavity pressed against a flat surface will create a suction effect and a resistance to being peeled off. So the same thing happens when you have several layers worth of enclosed space pressed against the PDMS layer at the bottom of the tank. when the part gets pulled away from the tank, the suction effect could actually rip off layers of the part, which could cause a total or complete print failure. So the simple fix for this is to reorient your part. So any of those enclosed cavities are only a layer or two deep. So remember that the deeper the cavity, the worse off you are. The other option is to reorient your part so that those enclosed cavities are facing the build platform. So I'll get into that a little bit in the practical demonstration, which is what we're going to jump into. Let me grab my mouse. All right, so let's get our hands figuratively dirty and jump into this. All right. So everybody see Preform on my screen? Okay, cool. So a quick little note about the interface here. We got the shortcut arrows there on the top right. One little note is you can hit this little eye icon in the middle or hit F on your keyboard, and that'll center your model in the screen. Over here on the left, we've got our support controls, and let me just pull in a model right now. Fresh. Okay, so now we have all of our support controls activated. Most of these are pretty simple. You generate the supports for the models you have selected. If you don't have a model selected, you'll have the option to generate supports for all the models in your scene. These are direct edit, so this button here, edit, allows you to directly edit the support placement for each model. Clear lets you wipe them away. Density changes the amount of supports, and point size, like I said before, is increasing or decreasing that touch tip size, which is increasing or decreasing the strength of the bond that's actually holding the scaffolding to the part. Below that, we have internal supports. I'll get into that in just a couple seconds. But basically, that's allowing the model to preform to generate supports that build off of the model geometry itself. Below that, we have the Advanced tab, and we also have this little refresh button. This will reset all values to default. So you can see, drag density all the way up. I'll hit the refresh button, goes back to 1. Below this, we have flat spacing under the Advanced tab. This is basically a measurement of how many points per X millimeters. So you notice as I increase the density, I get 1 point every 2.5 millimeters, whereas if I decrease the density, I'm getting 1 point every 7.5 millimeters. So it's just a little bit of extra info that you can use. Below that, we have the slope multiplier, which changes how many supports are on a slope face. Most of these you don't really have to change. That one especially, I've never had to change it. But below that, we have base thickness. This is actually pretty useful if you have trouble with non-adherence. You can increase the strength, the depth of the base. That will increase the bond, but make it harder to remove. If you decrease the strength, it'll make it easier to remove, but you'll end up with some wobble, or you might end up with some wobble on your part during the print operation. And then finally, height above base. That's pretty self-explanatory. That's how high the part is above the base itself. Okay, so the reason I pulled this cup in here is I wanted to show you guys what it looks like when you have a part that will have an enclosed cavity. So the first thing you should always do before printing is go over here to the right side of the screen. There's a slicer bar, and you should just drag through each layer of your model. And you can see here, remember, this is inverted relative to what the machine will actually put out. So the build platform is the grid on the bottom, and the resin tank is up here at the top. So as I drag through this, what we're looking at here is this part will be printed, and you have this huge cavity that's pressed directly against the resin tank. And unfortunately, that will cause delamination. So how do you fix this? The easiest way to do that is to simply reorient your model. So I'm going to go to the orientation tool, and I'm just going to click and drag in the workspace. And now that the model is facing the hole, or sorry, that cavity is now facing the build platform, which again is the grid. If I slice through it, you see I have no enclosed cavities, and now this model will definitely print. Once I get to this point, it closes itself off, but don't worry, because we actually have this big hole in the front that allows that air to escape, and we won't have a suction effect. The other thing I said I would get into is internal supports. So I'm going to pull up 2 copies of this cup. One with internal supports. So I click the layout tool, I'm going to drag that over, and I'm going to add one without internal supports to the scene. Okay? So what does an internal support look like? Basically, if we slice through the model, I'll let the computer catch up. So over here on the left side of my screen, you can see that some of the support geometry is actually building off of the model, where on the right side of the screen, there's none. So this could actually have a detrimental effect, and I'll show you. I'm going to jump into the support tool, like this, go into supports, and go to edit to manually edit support placement. And the reason I'm doing this is just so that Preform will regenerate whether or not the model is supported. I'm just going to add a support. You can see a little blue bar at the top. That's Preform basically calculating whether or not the model is supported. And you can see I have all this internal area that's unsupported because I don't enable internal supports. So when it comes to internal supports, you have kind of this duality. On the one hand, do you need parts to be supported off themselves? Or on the other hand, how difficult is it for you to actually get in there and remove those supports? One thing you should, of course, you should definitely orient your cavities towards the build platform. But when it comes to supports, that decision is really up to you based on a per model basis. So I'm going to discard these edits. I'm going to clear the scene here. I'm going to move on to the next example. So I'm going to open up flat sheet. So one question we get all the time is, how should I print a flat model? On an FDM machine, it makes sense to just print it like you see here. With an SLA machine, the answer is a little bit trickier. So this would print fine, but in order to get our parts to adhere to the build platform, one of the things we do is we overcompress the first couple layers of the print. The reason we do that is so that when it's a base, it's basically smashed up or smooshed, to use a more delicate term, up against the build platform, and that's ensuring that it'll stick on there. When it's a base, that's usually not an issue, but when it's a part, let's say this part has to be 3 millimeters, it might end up being 2.5 or 2.75 millimeters because of that early overcompression. So what you want to do here is you want to orient the part upwards. So I'm going to go to the orientation tool, I'm going to click and drag. And one other key thing I'm trying to do here is get the part to orient off itself, to build off itself, and minimize the surface area per layer. So as you can see, as I slice through this, I have very little surface area per layer, whereas with this option, seem to have lost my little slicer bar thing. There we go. With this option, you can see that I have a ton of surface area. So you want to avoid that sort of scenario. The other thing here is that you want to orient it towards the front of the machine. So I'm going to open up a pre-supported version of this model. And then I'm going to go to the layout tool. And you can see it's already oriented properly, the front side of the machine and the wiper side. We want the long axis to be oriented towards the front of the machine. You can actually adjust this pretty easily by holding Shift and pressing right or left arrow. And that'll rotate the model on its Z or vertical axis. The other thing here, and the last thing I'm going to show on this particular example, is support orientation on corners. So what we have here is Preform's default support, and it works, but we can do better by doing it manually. So if I go to the supports tool, I go to edit, I'll enter the supports edit mode. By left-clicking on a support, I can remove it. Or by box selecting a support using the left click, I can remove all of them. And then you want to zigzag your supports on any corner. So you want to support both sides of that corner. And you notice how much fewer supports I'm actually using. So I'm going to hit apply. It's not a lot of supports, but let's see what the Preform says. Look at that. Except for this one spot here, the model's fully supported. So I could probably just add that in. Extra little one right there and there. Hit apply. And I bet you that'll go away. So really what you're trying to do here is you're trying to not only minimize the amount of supports you have, but also support both sides of that corner. And that'll give you a much sharper edge and a much more reliable print. You won't have to snip supports off of the corner itself. Okay? So on the topic of supports, you can actually generate your own outside of Preform. So I'm just going to show an example here. So on the left, I have supports generated by Preform, and on the right, I have that model without any preform supports. This is some sort of ring or something like that. This sort of technique is really useful if you're building very small or very fine parts. You can generate your own supports using your CAD software. This sample ring was done in Onshape, and the support that I generated is just a simple sweep. There's a circle swept along a path with a small chamfer and a fillet on the very tip. And you can see here, I'm just going to go to the edit mode, add one, and then remove it. And you can see that I'm supported on this side with my custom support, but I'm not supported on the left side. So you can actually build it so your models print flat on the build plate with supports and not have to have Preform generate them. If you had Preform generate them, you would have to have the model on some sort of base. So this is an advantage to using this system. So finally, we're going to jump into a person, or not literally into them. We're just going to bring in a 3D model. And we've got this person here. So what we're looking for here are islands and local minima. So islands are any part of the print that's going to be part of the model at a later layer, but on earlier layers they're isolated. So for instance, these arms are islands until they get up to the shoulder. A local minima is the lowest part or lowest point on the model in any localized area. So for example, the local minima here would be the index finger of this person's hand. Over here on his feet, it might be, the bottom of his foot. But that local minima also has to be supported. So when you're inspecting your model, you want to slice through it to make sure that every local minima and all the islands are fully supported. But you heard me talk earlier about orienting your model so that it'll build off itself. So what do I mean by that? This is a really great example. We have this person here. I'm going to bring in a properly oriented example. Jobs. And you can see, oh, it looks a little silly, but one key difference here is that his hands don't have any supports on them. Whereas on this guy, if you try to snip these supports off, you might take the whole finger with it. Whereas this guy, his hands are actually building off himself. And you can check this by going to the slicer bar and just dragging up through the bar and just see that there's no isolated areas. Any isolated areas are going to need their own supports. But if you angle your model so that when you slice through it, it's a continuous growth, you don't need it anymore. In addition, you also don't have to worry about removing supports from hard-to-reach areas like under his shoulder, like under the armpit or anything like that. Finally, this is just a bit of advice. Whenever you're printing a person, we found the most success to be with somebody who's upside down at like a 30 to 45 degree angle. So let's jump back into the presentation. What happens if after all that you still have some sort of print error? Despite your best intentions, stuff does go wrong. So we're going to talk a little bit about that and how to fix those problems. The first one, we see this one a lot, is explosions. They look like a vaguely conical shaped chunk that's missing from your part, and it emanates outwards from a single point. As you can see here, they're caused by a piece of cured resin getting stuck to the bottom of the tank. So as the layer passes over that area for the next layer, the puddle of cured resin kind of grows slightly because, again, remember the laser passes over the previous layer and the next one slightly. So you're growing this kind of you're creating this ever-growing pocket that you can't, the laser can't penetrate through. So that's what causes these. The easiest way to fix them is to just reorient your part. So slice through it to find any areas that are unsupported. Again, especially those local minimums and islands. If you reorient it a couple times and still don't have a solution, you should check the bottom of your resin tank or your optical window, because sometimes dirt on these sensitive surfaces, they can cause the laser to improperly cure a section of layers. So make sure your stuff is clean and try reorienting your model first. So breaking away from supports is another very common issue that we see. It occurs when a model is improperly or under-supported or when the touch points are too small. So if you've adjusted any of the default settings, you should try and go back and reset it to like the normal size. Typically, I think the default is 1. Actually, yes, it is 1. You really shouldn't vary from that too much unless you have a specific issue. So unless you're getting non-adherence, so you could like increase it slightly, or unless you're getting like just too many supports on the part, you can decrease it slightly. So again, with this, try changing your settings back to default. Try increasing the touch point size. That might help. Try increasing the amount of supports. And then make sure your model follows the support rules. So, don't orient a long piece that's parallel to the build plate. Like I said before, you want to minimize the surface area per layer, and then try and make your model build off itself as much as possible. Delamination is our next one. It's characterized by one or more layers peeling away from the others. It's relatively rare, but it can happen when a tank or optical surface is dirty or damaged, or your build platform is actually loose. An improperly supported or oriented part could actually also play into seeing delamination in your prints. But the most common reason for this is when a print is stopped or paused for several hours. So in a Form 1, if you have a resin fill-up pause that lasts too long, or if you have a Form 2 and you pause it and you just walk away from the machine, that can cause that. So before starting, make sure you have enough resin in your tank. Make sure you're there to refill it. Don't let it sit. And then make sure you're not using any old or clouded tanks or your optical surfaces aren't dirty, because again, those could cause this. Oh, one last thing is that your build platform being loose could also cause this. So double check your build platform and make sure it's tight. So you can just wiggle it. If it wiggles in your hand, then it should be tightened. Contact support will send you the instructions you need. So lastly, partial or complete non-adherence is mostly something that occurred with the Form 1 or 1+, but it can still occasionally come up with a Form 2. So if you see if you have a dirty optical window, if you've tried a different tank and the tank it's still not doing it, then the tank might have a PDMS layer that's slightly out of whack. So basically, double check the cleanliness of your tank, your optic windows, all of those things. Make sure your material settings are set to the proper resin. You can try increasing your base height, like I mentioned before. That'll provide a stronger adherence. And then lastly, if that problem started when you tried a different tank, try fine-tuning the z-axis of your printer. You can adjust this downwards in 1/4 or 1/2 millimeter increments, but you should definitely only try that after you've tried all the other steps. So as we wrap up this talk and before we get to the Q&A, I'd like to spend a few minutes talking about resolution and how it pertains to Formlabs machines. So there are 3 factors that go into a 3D printer's resolution: X, Y, and Z. X and Y are the flat resolution, and then Z is the one you're probably most familiar with, where it's vertical. Let's start with X, Y, and then we'll get into Z a little bit. But as you can see in the graph here, the measured versus intended, so the measured is blue, and the ideal, which is the CAD model, is orange. They don't intersect until about 150 microns, which is our minimum feature size. So way we tested this, there's actually a great blog post. You can follow the bit.ly link on the slide. But we had a block of material that had lines kind of cut into it at different intervals, and each line was slightly bigger than the rest. So if you have a line that's 0.15 millimeters across, it will print. If it's less, you're going to end up not printing quite. It's not going to come out quite as well. The other thing here is, before I jump into the z-axis one, I just want to say, for comparison, an FDM machine, you're looking at 0.3 millimeters or 300 microns. So again, the line will have to be twice as big in order for it to show up on an FDM machine. So it's one of the advantages of the SLA process. Of course, moving on, once we get into the z-axis, the SLA machines are also better in that. A little bit more resolution there. For us, our minimum height is 0.025 millimeters or 25 microns. So that means that each of those lines could be cut a minimum of 25 microns deep before a Formlabs machine could resolve them. For comparison, an FDM machine tops out at about 0.1 millimeters, which is about 100 microns. So it's a huge leap in comparative results. However, before I move on from this slide, that is our minimum dimension, and we really recommend that it's only used for very small and very fine parts. In fact, we actually have a special castable setting specifically for jewelry that's optimized for fine detail. For the majority of our other parts, however, we recommend about 50 microns. So for large parts, especially ones with with flat sides, we really recommend 100 microns. Remember, these settings are for layer height. So unless you have a feature below 50 microns in height, you won't notice a difference between 25 and 50, other than a relatively small increase in smoothness of the part. So if you're interested in learning more about this stuff, we have a bunch of design guides online. 50 microns we recommend because it will also give you faster and more reliable prints. 25 microns is more susceptible to laser bleed over time on a large part. Small parts, it's fine, but on larger parts, the laser might penetrate through the resin a little bit extra. So if you have a circle it might be like slightly flattened on the side of the circle that faces the bottom of the tank. So again, if you want more detail about this, you can go online. But right now, I'd like to take the time to open up the floor to some questions from you folks. If your question isn't answered in time, you can feel free to shoot us an email at announcements@formlabs.com. So I'm going to take a look. Let me just get a second here to pull up the questions that have been asked. Okay. So how accurate is the laser to print circular patterns, like less than 1 millimeter diameter? Does the laser generate some kind of error in the printing between both sides of a circle, for example, so that it may lead to a overcured in a closed circle? It doesn't look like that. The full text of that question came through. So basically, oh, here we go. So it may lead to an overcured in a closed circle. So like I was just saying, when it comes to the laser for very small parts, so like for instance less than 1 millimeter in diameter, you can use the fine detail setting 0.025, 0.05, sorry. You won't experience that sort of overcuring. Like I said, the 0.5 is more reliable when it comes to avoiding those things, especially the bigger you get. So does the laser generate some kind of error in the printing between both sides of a circle? Well, I think what you're asking about is tolerances. And tolerances are basically, for those who don't know, whenever you make something in real life, it's going to be slightly different than the CAD model. You will always get some variation. I don't have the specific number in our head for our tolerance, but I think if you were going to print something, you could roughly rely on 0.15 millimeters as a variable tolerance. That being said, if I remember right, our design guide recommends 0.5 millimeter clearance between any parts that have to move. So if you have two sets of gears, you should keep them 0.5 millimeters apart. Okay, so every time I open a Preform project, it has a different parameters to the default values. So it's not possible. It is not possible to make little changes after you have saved some work and open it again. It's a way to avoid this. Yes. If you save your model, so I think I get what you're saying. Basically, every time you open Preform, and I can actually experiment with this on my screen. Let's see. So I go to the Supports tool. Yeah, so it looks like when you open a model, it doesn't keep the settings from the previous job. For that, I'd really recommend saving your model so that it so that you can keep those settings, and then you kind of just remember them in your head. That's the best advice I can give you for that one. What's the best way to store resins after use? I will be switching many resins, and I have resin tanks. Each tank will get its own resin, so not to mix. Very good. Would covering them and placing the resin tank and with resin in a dark place work? Yes, that's no problem. You said not to clean the orange plastic with alcohol. What do you recommend to remove resin from surfaces in general? For everything except the orange plastic, you can use IPA. For the orange plastic, we recommend Novus 2 and then Novus 1. You can find it on Amazon. Can STL files be sent straight to the printer without going through Preform? I need to introduce porosity into my structure, but the Preform software does not perform this to the STL software. My other 3D... Oh, so when you're talking about porosity and you're saying your other 3D printer software does this, I'm assuming you're talking about an FDM machine, and that porosity is actually called infill. Due to the way that the machines work, it doesn't happen. Our SLA parts are cured as a solid block. FDM parts have an infill, which is that porosity you're talking about, where it's like a hexagon pattern. That's there to increase time and decrease material usage. If you want porosity in your material, in your part, I recommend, I don't know what modeling software you're using, but I recommend just adding it manually using your modeling software. There's some stuff like Mesh Mixer has an option to create like porous models, like with that sort of, but I'm not sure if it's what you're going for. You can also just try like extruding something. If you're using like a NURBS-based package like SolidWorks or Rhino, you can extrude the surfaces through the model and use them to cut out chunks. But it's one of those things that unfortunately the process doesn't lend itself to what you're doing. I think if I had a little bit more detail, I might be able to answer that one better. Is it better to use the quick print option for Preform supports? I imagine it's generated by the Preform algorithm, so it can be a better option. Yeah, I mean, give it a shot. I find that it's usually pretty conservative, so you can actually sometimes get less, but by doing it yourself. But I've printed some complex models with that, and it works just fine. So, oh boy, lots of questions. Is it better to leave the part in IPA for longer than the recommended 10 minutes? Will I harm the part if I leave it in there for 30 or 40 minutes? It depends. If the part is very thin, then yes, it will start to kind of get soft and degrade. So you want to avoid that. If the part is just a big block of material, then yeah, it should be fine. I already answered that one. The issue with both sides of the corner is one side may need to have a smooth finish after printing. How would you orient that? I might want to tilt it back slightly so that one of those corners doesn't need to be supported. Again, you're just trying to orient so the part builds off itself. So if you can find some sort of orientation where that area is not doesn't have supports on it, but is still fully supported, that's fine. Just remember, try and minimize the surface area per layer. I have found a huge difference between the basic gray and the basic black resin when it comes to clean removal of supports. I'd like to hear this addressed. Our different resin formulations have different properties. Sometimes it's easier to remove one than the other. You can. What I would recommend, if you really like to get more info on this, is just send an email to either announcements@formlabs.com or send one to me, Jordan@formlabs.com. I'll try and get it answered for you. I don't have the technical expertise to really answer that question effectively. I've noticed that since the last firmware update, the support material is more flexible and easier to remove. Was there a change to how the support material is cured? No, not to my knowledge. We made some changes to increase the adherence of one of our resins. I think it was Flex V2. But aside from that, I haven't heard anything about changing how the support material was cured. I have to print my design and parts using flexible resin to I have to print my design in parts using flexible resin to complicate support. Can I glue them together afterwards? Yes. You can glue them together. Again, if you have a handheld version of a 405 nanometer wavelength laser, again, you can pick those up on eBay. Just search 405 NM laser on Amazon or eBay. If you dab a little bit of uncured resin and put the part together and hit it with the resin, it should work. I've also found personally Gorilla Glue has successfully glued one of my parts to a wooden base. So you can try that as well if the first one doesn't work out for you. Can you talk about mixing resins? I've heard a lot of people experimenting with 50-50 or 80-20 tough resin. I can't say too much about that. I don't know. My best guess would be going the forums. What I would say is you really want to run your printer in open mode because once you're changing the ratio of the resins, you're changing the viscosity of the resins, and you might end up with a situation where the part actually kind of like the resin flings itself out of the tank. So best thing for that would be to ask our community. They'll have a lot more knowledge than me. We print trays of very large jobs overnight, and I'm afraid to leave a cartridge in when the printer is telling me it's low. Is there a way to empty the cartridge into a new tank so it's not wasted and I don't risk a print stopping overnight? Yes, just make sure that it doesn't go above that fill line that already exists in the tank. You can see it in the front. Try not to, add too much resin to the tank so that it goes over that. Is there a way to post-cure clear resin without it yellowing? Because that's an issue I've always had during post-curing clear. I know there was some yellowing issues with earlier versions of our resin. The V2 or V3, I think it's V3 out now. I don't know which one it is. It's a lot better, so I would recommend trying that. But if you're using the older ones, I'm not sure. Try a cure box, actually. I think that would probably help. Again, you can check out our website to find out some solutions for that. So with the that's not a question. Is there outgassing of a part after it is post-cured? I have noticed a part will initially stick with super glue, and then after a day or so, the part might fall off. That's a very good question. I'm not sure, to be honest with you. Best would be to either email the contact form on the slide, announcements@Formlabs, or post on our forums. That would be my recommendation. Which is the best way to print some features that have some depths? For example, a box has holes with depth embedded on the model. Is that the same way with the cup example? Yes, I think I understand what you're saying. If the box is basically a solid box but with holes in it, those holes should be pointing towards the build platform, but slightly outwards so that air can get in and out. What you're trying to avoid is in a completely enclosed cavity. So as long as you're avoiding that, it should be fine. Since IPA is bad for the tank, how do you clean it? Novus 2 or Novus 1. I think there's some instructions online on our support site on how to clean it in more detail. I've been using a 40-watt black light for post-curing. It definitely works, but I have no idea how well. It usually takes a couple of hours before the resin is drying hard. Any comments? Add some heat and make sure your black light is using that 405 nanometer wavelength if possible. That'll definitely increase your effectiveness. And one addendum to that is to make sure it's at like 60 degrees Celsius. So I'm going to answer a couple more questions. It's looking like we're getting close to 2 o'clock. I'll try and answer like maybe 3 or 4 more, and then I'm going to have to say goodbye for now. I have a Form 1 Kickstarter and also a Form 2. I read resin for the Form 1 is in limited supply. Any estimates on time before the Form 1 will be useless, however, providing an unofficial hack so we can use them for projecting a laser show on the ceiling with the orange lid removed. Actually, one of our engineers did that without galvanometers. They made a game of asteroids using the lasers from the galvos. So it's pretty cool. It's possible. I would suggest open mode. As for the resin for the Form 1 in limited supply, I haven't heard that. The resin that's the Form 1 and the Form 2 use for the most part are the same, so I don't think that's going to be the case. As for estimates on time for how it'll be useless, I don't know. I can't tell you. I'm sorry. Is there just going to be a German version of Novus Cleaner? I'm not sure. You should still be able to get it on Amazon. I'm pretty sure they'll ship internationally. Does the worm drive need to be periodically greased? No, not unless you're getting some sort of noises from your machine. Any more plans for color choices or colorant? I can't say. I don't know. Sorry. Can I get in touch with your team about using a Form 2 resin for a research project? Yes, send to announcements at formlabs.com or send to Jordan at formlabs.com, and I'll put you in touch with the right people. How stable is the post-cure tensile strength? All right. I'll answer this last question. It's going to be the last one. I lost it. How stable is the post-cure tensile strength over a period of time, like a year or 2? I honestly don't know. That's a good question. Post to our forums. I'm sure some users will have some answers for you. Thank you guys so much for coming. Again, big thanks. That's going to wrap it up for now. If you sign up for this webinar, you should be getting an email with the recording. We'll also be putting the recording online. So thanks again for coming, and again, happy printing.